All right, let's start off with the 13.1 notes with what is probability. So probability, we use that word sometimes. It kind of means the chance something might happen. But here in math class, it's a numerical value from 0 to 1 that measures the likelihood of an event. So rather than saying like, oh, it's likely to storm later, that's not really probability for us. We're looking for a numerical value. So that could be something like a 6 out of 10 chance, could be a 60% chance of rain. It could be a 0.6 chance. Fractions, percents, decimals, all are fine. The only thing I ask is that you change fractions to be simplified. Okay? So we're talking about theoretical and experimental probability today. So theoretical is the likelihood of an event based on mathematical reasoning. So whether that means we are counting up a certain number of events, listing probabilities, counting combinations, that would be theoretical. So anything we're doing with pen and paper, we're not actually going out in the field and testing anything. So, for example, pretty simple example, if we have a 6-sided die, what's the probability you roll a multiple of 3? Well, theoretical probability means you basically write out all the outcomes and copy down how many of those outcomes are a success. In this case, 2 out of the 6 are a success, which is also 1/3. So this is theoretical, since we are not actually rolling die and like counting and making tally marks. We're just writing out the outcomes and doing the math. So an even number would be 3 out of the 6, which is 1/2. So 50% chance when you roll a die, you get an even number. Okay. So a deck of cards, if you look on Schoology, I posted a photo of a deck of cards. You can also search on the internet. You might have a deck at home. But basically, there are 4 suits and 13 ranks. So a rank is like a number. So like an ace is 1, you got a 2, 3, up to 10, you got a jack, queen, king. There are 13 cards in that range. And there are 4 different suits. The suits are diamond, heart, both of those are red, and we have a spade, which looks something like that, and then we have a club, which looks something like that. Those are both black. So the probability of getting a diamond is 1 out of 4, because the diamonds make up 1 out of 4 of the cards. There are 13 diamonds, 1 out of 4 suits. And then if we wanted to find the probability of getting an ace, well, there are 4 aces in the deck of 52 cards, which is 4 times 13, which could be simplified to this. But, this makes sense to us too. Aces, it's 1 of the ranks out of 13, right? So as long as all the cards are in there, that's what we would expect. If we start pulling cards out of the deck and we only have like 49 cards left, our probabilities are going to change, right? Depending on what was picked and what you have left. Okay. So let's say we have a playlist of some songs. You got 30 songs. All those added together. And what's the probability you get a lo-fi song if you hit shuffle? Well, there are 5 lo-fi songs out of 30, so a 1/6 shot that you'll play a lo-fi song when you hit shuffle at the very beginning. Now, probability that it's not a rock song, well, you have your pop songs, you have your lo-fis, and you have your hip-hop. If you add all those up out of the total number of songs, we get 20 out of 30, which is 2/3. What's interesting about this is this number here is also the same as 1 minus 10 out of 30. Well, I guess easier to see that's this. So the probability of a rock song is 10 out of 30. So the probability that you're not a rock song is you subtracted away from 1. And remember, 1 is 100%. So 100% of your songs, if you take away 1/3 of that, you're left with the songs that are not rock songs. So a few different ways you could do this. This is called the complement when you take away from 100. Because the probability of all your stuff, it's got to add to 100%, right? You can't have, everything, it needs to be accounted for. Okay. So we're going to do a little experiment in class on this exact thing right here. But when you roll 2 die, you got to kind of imagine that you have 2 different colors of die. You got, a purple one and a green one. And we want to try and find out all the different combinations of dice, right? Turns out that there are 6 different possibilities here and 6 different possibilities here. So, and because those dice don't have any effect on each other, we multiply together and get 36. Also, you could see this visually, right? Let's roll a 1 with purple, and then there's all 6 of these that can go with it, right? If you roll a 2, you could get a 1, a 2, a 3, a 4. You see? So each one of these clumps is 6, and there's going to be 6 of those. So those are all your outcomes. So what's the probability of rolling a 5? Well, the only way you can get a 5 when you roll 2 dice together is by rolling a 1 and a 4 or a 2 and a 3. There's no other ways you can get a 5. But because we're counting up every single outcome, we include them, because this was the purple or the pink or whatever die here, right? So having a having a purple 3 is different than having a green 3. You see? So we're listing out all the possible outcomes. So order does matter here. So in fact, it turns out that there are 4 different ways to roll a 5 out of our 36, which is 1/9. Okay. And we'll look at that more in the experiment we're going to do in class. Hopefully you are there for that. So an experiment is testing for a series of outcomes with actual data. That's the key word here, is with both an experiment and with experimental probability. It's the likelihood that an event occurs based on the actual results. So this is in both the definitions. It's not about like this over here where we're like trying to figure out what are all the different ways you could, combine 2 dice together. It's not about that at all. It's just about doing it, right? Rolling those die, doing that 100 times and seeing how many you get of each, and then basing your probability off of that, right? Trusting the evidence rather than trusting the math, right? So it's kind of a battle for that. Which one's better, theoretical, experimental? Some things you can't theoretically do. One example in class was we talked about the probability of you going out on a football game and getting hurt. You know, that's not something you can sit behind and calculate. The only way you can get an answer or probability of that happening is looking at past data or past occurrences, right? So maybe out of 15,000 games, 1,000 people get hurt, or there's 1,000 games where someone gets hurt. That gives you then a probability, right? Theoretically, you didn't really do any math calculations or reasoning, right? You're just counting based on evidence. So experiments are all about evidence from the actual real world. Okay, so I got 2 examples of that. We got a quality control inspector who's got 500 monitors and finds defects in 3 of them. So according to just that experiment or that sample, the chance of picking a monitor that's going to have a defect is 3 out of 500. Okay. And if you want to, that's a percent, right? You can convert that to a percent if you want, because it's equal to this as a decimal. Remember, we moved the decimal place over. So I write it as a percent because I think that's the easiest to see, right? They have all these monitors now, and we want to know how likely is it, how many of those are going to be defective? What can we expect? Well, you would take that percent that you found and do of that number, right? And the math for that would be, you take that fraction, and of means multiply, times the total. So I got approximately 91 defective monitors. So we had no idea how many were going to be defective, but we did an experiment and said, hey, let's look at 500 and see how many of those are defective. Okay, and then we found the experimental probability from that, and then we used that to predict the future. Okay, so this happens all the time. So imagine there's a park and there's loads of trees, and you want to figure out how many are maple trees. You might just choose to not drive yourself crazy and just look at a sample of just 40 of them, right? So say you find out that 25 out of 40 are maple. So that's 5 out of 8. Okay, that's experimental probability. That's what you found. Okay, and this says how many trees are likely to be maple. Well, 5 out of 8 of them. Out of what? Out of 538. So we're banking on the fact that our sample was representative, and it really represents the whole park. It has a good mix of trees. It's not just all these, certain trees in the corner, right? So we're banking on the fact that all the trees in the whole park look similar to what was in our sample. And that was 5/8 of all the trees are maple. So this is approximately about 336 maple trees. Now, does that mean there are exactly that many trees? No, it doesn't. In fact, it's pretty low chance that there's actually that exact number. There might be 340 or 330 or maybe even 300. His sample wasn't that large. He only looked at 40 trees, right? So, for example, if this was 22, that would drastically change our final answer, right? So a small sample sometimes doesn't cut it. We have to make sure we're doing enough trials, and that takes time.